friends, welcome to the course on electronic packaging and manufacturing. This is vibration analysis 2. In the last lecture, you have learned about the importance of vibration analysis, namely the vibration testing, and you have also known that the vibration testing is quite important from the reliability point of view. Because of vibration, the electronic component, specifically the joints, may fail due to fatigue or due to excessive deformation or maybe due to the excessive displacement leading to the collision of the components. Now, in this lecture we are going to learn something about the basics of vibration analysis. So, here in this course you will in this lecture you will learn mainly these following points: the transient and steady state response, force transmissibility and motion transmissibility. These are very important concepts which we will learn slowly. Now, first of all, in the response analysis we have a vibrating body and which is subjected to loading. Now, this loading can be from outside or that is from the force or from the displacement. So, in the first case we will call force loading, and in the second case we will call displacement or the motion loading. Now, during this loading process, the transient response also plays certain role as well as the steady state response. In the steady state response, normally the excitation level can be different, and in one type of excitation which is very important from the electronic packaging point of view, that is the random vibration. Let us learn something about the response analysis. So, let us first consider the response of an electronic package which is in the form of a spring and a mass and another casing which may have certain substantial mass. Let us consider this mass to be capital M and this mass to be small m, whereas the spring stiffness is K. Now, suppose that this is getting dropped from a height h. Okay. So, in that case, when the body falls, then it acquires the velocity v, which is equal to 2 g h. Now, after it touches the ground, then it may rebound back or it can stay for some time. Now, as it so this depends upon the nature of the collision. Supposing that the box remains stationary when it comes to this position, then the equation of motion of this particular mass will be written as m x double dot. This is the mass times acceleration, and that is the equal to the total force, and for this mass the total force will be equal to mg, which is the weight, and plus k and x minus L, where L is the free length of the spring. Now, so you write down this one mg minus k and x minus L. So, it comes with a velocity v, and then after that when it reaches the bottommost point, that is the box touches the ground, then it starts vibrating. After that there is almost no force, but only the force due to gravity, which is a static force. Now, you will see that for some value of x, x dot and x double dot will be equal to 0, and that value we will consider to be the equilibrium value, and that is equal to minus mg. This is x equal to L minus mg divided by k. So, this is the value where x double dot will be equal to 0, and this we will consider to be the equilibrium position. So, what will happen, because of this self weight, it will have in the equilibrium it will be displaced and the spring will have certain deformation. Here of course, I measure x as the distance from this bottom point to the mass. So, this is the equilibrium position, and if you consider the displacement around the equilibrium position, that is this plus x dash say, then the equation of motion around the equilibrium position could be written as m x dash double dot plus k x dash equal to 0. So, here you will see that this is the equation of motion of free vibration, and it has its velocity. So, velocity, what will be the velocity? The initial velocity is x dash dot at t equal to 0, this is equal to v, the velocity with which it is touching the ground, and then the displacement x dash 0 is, let us say, its displacement will be equal to x dash. So, some displacement which I call to be, let us say, 0. Now, what is going to happen in that case? So, this becomes actually the equation of motion of vibrating system, just single degree of freedom system with a mass and the stiffness k, and this is the free vibration problem with the initial velocity v and the displacement 0. Now, let us see what is going to happen to this. So, here, so if you plot x versus t, x bar versus t, then what is going to happen? Because of its velocity, it will start oscillating and it will keep on oscillating. So, this is the time period of oscillation, which is t, and that is t is equal to 2 pi by omega n, where omega n is the natural frequency under root k by m. And you have seen that if this is the delta is the static displacement, then this is equal to actually the static displacement, it was equal to x minus x bar minus L, and which is equal to m g by k. So, from these two results we can see that this will be equal to omega n is under root g by delta, where delta is the static displacement due to its own weight. Now, what will happen if there is a damping? Remember that I took only the spring and the mass. Now, if I take another damping over there, then depending upon the coefficient of the damping, then two things may happen. Either the damping, if the damping is low enough, then what will happen is that this will keep on oscillating, but it will eventually die down. So, this is the case for the underdamped situation, and if the damping is quite large, for example, here, then it may so happen that it will decay without oscillation. So, this is the case of undamped system, this is the underdamped, that is C is low, and this one is the overdamped, C is high. So, this is so far as the stationary, that is the transient response is concerned. Now, when we have a steady state motion, that means let us consider now the situation where we have again similar box, and this is actually the box, and this is connected to a table, and this table is actually getting vibrated with a certain motion y t. Then what is going to happen? So, here if I consider x t, and and this x t, suppose this x t I measured not from here, but let us say this is our x t, that is the measured from the base. Then the equation of motion of this case will be equal to m, the absolute acceleration of this body. Absolute acceleration will be x double dot plus y double dot, because x is the relative x double dot is the relative acceleration with respect to this moving base, and y is the acceleration displacement of the base. So, therefore, the absolute acceleration will be double dot, and that is balanced by the force minus k x, and this gives rise to this equation m x double dot plus k x equal to minus m y double dot. So, this is the generic situation when we have the base moving with certain acceleration. Now, let us consider the case, the simplest case is y is equal to y, let us say cosine omega t. That means, that is we have the harmonic excitation given to the base. In this situation, y double dot will be equal to minus omega square y cosine omega t, and then to find out this x, actually x, the response will have two parts. One will be the transient response and another will be the steady state response. Now, eventually what will happen, that this transient response will go to 0, because there will be always certain damping present, even if the damping is very small, so that the steady state response is not sensibly affected by it, but there will be always certain damping, and that will lead the x transient to go to 0. What remains is the steady state solution. Now, the steady state solution, we express the steady state S s as, let us say, x cosine omega t in this particular form. Why this cosine omega t? That is because since there is no damping, so these two motion, that is y and x, they will be either in phase or out of phase. Now, it is a very trivial exercise to substitute this into the equation of motion and find out the value of x. Now, what will happen to this is, this x will be equal to then omega square y m omega square y, and this divided by k minus m omega square. So, this after rewriting, it will be y times omega square divided by omega n square minus omega square. So, now you see that the x, this one will behave something like this. If you plot mod x, there is a possibility that the denominator here becomes negative. So, in order to avoid that, we consider only the modulus. When it is negative, it is actually out of phase motion, and when it is positive, then y and x, these are in phase motion. Now, what will happen when omega is very small? So, if I place this with omega, then what is going to happen when, so when omega is very small, then it is approximately 0, whereas when omega is quite high, then it reaches this value 1. This actually this divided by y, let me consider. So, you will now see that when the excitation frequency is near the omega, then omega n, then actually the value of x becomes infinitely large. Actually, what happens then, there it becomes the resonance. So, there is a phenomena resonance, which is very important from the vibration point of view, and during resonance what will happen, the response will build up to infinity. Otherwise, the response will be bounded, and we have seen that when here, when excitation frequency, let us say in this region, the x value becomes quite small, whereas if here it is omega, then x is of the same order of magnitude as y. In fact, when omega tends to infinity, then x and y become same. So, therefore, entire vibration is transmitted to the body. Now, what we will see later on, that this x has something to do with the force which is being experienced by the spring, and in electronic packaging this spring will come in the form of the lead or other connections of the equipments to the packaging level. So, that will play a certain significant role. Now, what will happen when the damping is included? Then the damping is included, then actually this becomes changed, and we have in that situation, if we have small value of damping, then the response will be something like this. It will be bounded. So, it is not unbounded like this. So, we have certain value of damping, and if the damping is quite high, then it becomes like this. So, this is the high value of damping. Intermediate, there will be certain situations like this. So, if you increase the value of the damping here, then damping means that in this case I had the system and here there is a damper and this base is excited. Now, that is so far as the steady state motion is considered with the harmonic forcing. Now, if you have any arbitrary forcing, let us say y t, which is continuous, then we know that according to Fourier transformation, then y t can always be expressed as y omega and e to the power j omega t d omega. So, in this particular form, y omega is the Fourier let us say Fourier transform of the function y t. So, if the system is linear and we have already considered this part, that is the harmonic response due to that. So, using the principle of superposition, we can always find out the response due to any arbitrary loading, so far as this is continuous. But a different situation happens when we have a random loading. That is, if we have the random signal, then what happens? This consideration does not work, because the Fourier transformation of the random signal does not exist. And then, so in this case, what we are considering a signal y t, which is completely random, and we do not know how does it vary, but there is a technique of extracting certain continuous functions out of this random signal. What will happen, that if we consider, let us say, a function y which is known as the autocorrelation function, and this autocorrelation function is defined this way, minus t by, let us say, y t plus tau d tau, and this is the autocorrelation function. Autocorrelation function. So, this autocorrelation is a very well behaved function. If we consider the Fourier transformation of the autocorrelation function, then actually we will get S, and this will be equal to 1 by the Fourier transformation. So, therefore, this will be this 1 by 2 pi will not be there. So, Fourier transformation of this signal, this will be equal to r tau e to the power minus j omega tau d tau. So, this is actually known as the power spectral density. So, power spectral density, if we take the inverse Fourier transformation, then that becomes r tau, this is equal to 1 by 2 pi and s omega e to the power j omega tau d omega minus infinity to infinity. Now, sometimes instead of omega, which is the circular frequency, we write down in terms of the frequency hertz. Then in that situation r tau will be equal to minus infinity to infinity s is a function of f and e to the power 2 pi j j tau and d f. Now, r at 0, if you refer to the original definition, r at 0, this is actually the RMS value. So, RMS value of this function, this is nothing but minus infinity to infinity s f and d f. So, this part is actually the power spectral density function, and the importance of the power spectral density function is that as the if you integrate the power spectral density function over the frequency, then you will get the RMS value of the function. Now, in many situations when we have RMS value, that is in many cases the y is specified in terms of its RMS value. If we have f, then the RMS value of this thing, that means we consider SF, and in many cases the function is something like this. For example, when we in a standard testing protocol, we will have SF function is kind of this is increment is 3 dB, maybe this is minus 6 dB or so, and dB per decade, and this is a constant function. So, this is a typical SF curve. Knowing these SF functions, we can find out the response using the standard theory of random vibration, which is of course something which is quite deep, and I am not going to go into those details. Now, coming back then to this analysis. So, we have considered transient response, steady state response and the random vibration. Now, then comes the vibration transmissibility. Now, what is vibration transmissibility? That is, from the name it suggests that it is something which is transmitted. Now, there are two kinds of transmissibility, one is motion transmissibility, another is force transmissibility. These two are quite important. Let us now learn them one by one. So, let us first consider the force transmissibility. We have a vibrating system, and here there is the spring and the mass, and this is suppose excited by harmonic force F naught cosine omega t. Now, if you write down the force transmitted, that means what will happen, that during the vibration the spring will be deformed, and this spring deformation will transmit certain force to the ground. This is quite important from the electronic packaging point of view, because when the component vibrates, it transmits certain force to the ground, and this force is actually essential for development of the stress, and that stress, if it is quite large, then it may lead to the breakage of the component. Now, when you have the transmissibility, that is the force transmitted here. Now, the force transmitted in this case, actually we can find out the force transmitted F t as k x, and x you can find out from solving this equation m x double dot plus k x equal to F naught cosine omega t, and here you have x t, one can find out this as F naught divided by k, and that is equal to 1 minus omega by omega n square cosine omega t. So, here in this case you can find out this F transmission, F's transmissibility, this is will be equal to F naught cosine omega t divided by 1 minus omega by omega n square. Now, the transmissibility T f, the force transmissibility is defined as the magnitude, that is the amplitude of the force transmission divided by this force F naught. and which is seen to be equal to 1 divided by 1 minus r square. So, this is where r is equal to omega by omega n, it is called the frequency ratio. Now, let us see how the transmissibility behaves. So, if I plot omega by omega n, r equal to omega by omega n, and here it is transmissibility T f. So, transmissibility is 1 by 1 minus r square. What will happen when r is approximately 0? Then it will start from 1, and when r is equal to 1, it will go to 0. Well, interesting thing is that when r is equal to root 2, then also it becomes equal to 1. So, the curve will be like this and so on. So, this is the point root 2 and that is the point 1. So, you see that at the high frequency excitation the transmissibility becomes low, whereas during the resonance the transmissibility becomes quite high. Now, what will happen if damping is incorporated? Then the damping is incorporated, things may change. You will see when the damping is quite large, then damping is quite small, then what will happen, that this transmissibility will be like this. So, again it is interesting to note that for any value of the damping, the transmissibility will be equal to 1 when r is equal to root 2. If the damping is higher, then something like this will happen. If transmissibility is infinite, then it will be 1. So, if damping is increased, then we see two things, that is the transmissibility decreases in the resonance, whereas in the high frequency excitation the transmissibility increases. So, to reduce the transmissibility, that is the force transmitted to the ground, we need to have low damping if the frequency is very large compared to the natural frequency, whereas we have to have a very high damping if the frequency of excitation is very near to the resonance condition. So, this is important thing. Second, we come to the motion transmissibility. Now, what is that? Here we have similar situation, that is we have the mass, we have the spring, and then this is the moving part which is excited cosine omega t. The equation of motion, at this point we consider x to be the absolute displacement of the body with respect to certain inertial reference frame. Now, in that case the equation of motion will be m x double dot plus k x minus y, that is equal to 0, and in that situation x minus y. So, the transmissible x minus y equal to 0. So, m x double dot. So, in this situation actually you will get again the same thing, m x double dot plus k x equal to k y, which is equal to k y naught cosine omega t, and in that case the steady state response, once again you can find out that this is to be equal to y naught divided by 1 minus r square cosine omega t. So, here the motion transmissibility T m, motion transmissibility will be equal to the response amplitude, that means this part, that is the x divided by y naught and that, and this is equal to 1 by 1 minus r square and so. So, now we have seen that this is the same thing as the force transmissibility, that is it is not very coincidence, but it is true only for the linear system. If you have a spring, nonlinear spring, then for example, or if there is any nonlinear damper which may be always present, in that case the T m and T f will be totally different. This is here we call this absolute motion transmissibility. We can have also a relative transmissibility. Relative transmissibility is like this. Here we have the relative displacement x minus y, and the equation of motion, which is the original one, that is k x equal to k y, we can write down this way: m z double dot plus k z equal to minus m y double dot. So, this is the way we can always write down, and then this one become y naught omega t and omega square. So, there is an omega square term which will be appearing. In that case, the z, that is equal to, z will be equal to m, and this m will cancel out. So, therefore, this will be y naught omega square, this is equal to 1 omega n square minus omega square. So, that is what we have here. Now, again we now see that the motion transmissibility, and of course, we will have in that case m by k. So, this part, so the motion transmissibility will be now the z by y naught, that is equal to the motion transmissibility, but this is the relative motion transmissibility. If we plot the relative motion transmissibility, then this becomes like this. In the low frequency region it goes like this, and in the high frequency region it will be going like this way. So, therefore, this is T motion with the relative transmissibility, and here this is omega. Once again we see that at the resonance condition, the omega, that means that when omega is equal to omega n in this region, the relative transmissibility is quite high and very high. In fact, if damping is not there, it is actually infinite. In the low frequency region, T m is actually going to 0. That means, we will have a favorable situation in the low frequency condition, and remember that this frequency condition is a relative one. That means, it means that omega must be less than omega, very much less than omega n, that is in this zone. If omega is quite large compared to omega n, that is in this particular region, then we have a different scenario. We have that the transmissibility, relative transmissibility is approximately going to 1. That means, the base 1, the base and the mass, these two are having the base motion, and this motion is actually having the same thing. That means, whatever motion is being there, this vibration is actually of the same. That means, this is not moving at all. There is a phase difference, but now let us consider the damping. If damping is present, then again similar thing may happen. So, if damping is present, this will happen, and similarly like this, if for a very high damping, we will have this situation and so on. So, this is in the direction of the increasing damping. That means, here I have introduced one damping with a certain coefficient. Now, from the vibration point of view, transmissibility is very important concept, because we have to design the component or design the packaging, or design the connection in such a way that the motion that is generated in the base should not be transmitted to the equipment, or what is also important is that the force generated in this condition, in this place, will be small. and that will depend upon the relative magnitude of omega and omega n. So, suppose we want that the transmitted, there is a motion and we want that this vibration should not be transmitted here, then we can consider two things, that is, if the relative motion we want to reduce, then we have to design the system such a way that omega n must be omega n should be much high compared to omega. So, that it is in this region, whereas if omega when in the other situation what will happen, that this will become the vibration will be very large, whereas when we want to reduce the absolute motion of the body, that may sometimes lead to the collision of the systems, then we will have to design in a different scenario. So, here you have learned then the motion transmissibility and the force transmissibility, vibration and so on. So, in today's lecture you have learned how to analyze the vibration of a system with the force, without force, with random forcing, and you know the important concept of transmissibility. And in next lecture we are going to use this particular concept and see how this can lead to a better design. So, this part for today. Thank you for your attention.